Okay, so last time we discussed the thermofield double. The thermofield double is defined to be this state. So we are interested, if we're interested in the thermal density matrix on a Hilbert space H, thermofield double is a purification of that density matrix where we double the Hilbert space, and now we talk about the pure state beta in the doubled Hilbert space. The last thing I said at the end last time was that there's a sort of trivial isomorphism between operators on a Hilbert space H and quantum states on two copies of that Hilbert space H. And in terms of Bras and Ketz, it's very easy to see how you can map them. Don't confuse this with the idea of partial trace. That's something else. So the partial trace is a state, is a density matrix that you get on one copy of H after taking this state and tracing out the other copy. Okay. So now we're going to continue a little bit. Thermofield double, finish that up, and start something new. Any questions before we continue? Yes?
In that isomorphism, are you assuming anything about the dimensionality of H? Because if H is infinite dimensional, it's not necessarily true the dual is the same.
Yeah, good. Okay, so let me comment on this. All these manipulations that I'm doing of sums like this and thermofield double are formal. What I mean by formal is that they're not true. Okay, so these statements are true for finite dimensional spaces, and many of them are not true for infinite dimensional spaces, and many of them are not true in quantum field theory, and we're going to have to worry about that when we come to actually calculating stuff. It matters. But it works really well to pretend that it's true until then, so we're just going to not worry about it for now. Okay. Other questions? Okay. So the next thing we want to do is get the thermofield double from the path integral. Okay. I just erased it. Let's write that again. Okay. So I claim that the thermofield double as a path integral is just a path integral on a strip. Of size beta over 2. Okay, that should be slightly confusing because we already talked about the path integral on a strip of size beta over 2. And we said that this path integral represents the operator e to the minus beta h over 2. Right? So this path integral we said represents the operator because it has an open slot at the bottom for one of the legs of the operator and an open slot at the top. And indeed, if we put in field data at the top and bottom, we will calculate matrix elements of this operator. But the point is that it also represents the thermofield double state because they're related by this trivial reinterpretation. Okay, so if we want to interpret, so the point is that we can either interpret this path integral as the operator from H to H, or we can interpret it as the state on two copies of H. And so we should interpret one of these cuts as being one copy of the Hilbert space and the other cut as being the other copy of the Hilbert space. Note also that this, as an operator, is the square root of the thermal density matrix. It's e to the minus beta over 2 times h. I'll leave it as an exercise to just think through yourself and check that the matrix elements calculated by this path integral are correct. Okay, so we're just reinterpreting the two cuts as being one state. Yeah.
So the state has like a get structure,
Yeah.
and the operator has a get prop.
Yeah.
And do you have to complex conjugate something in the path integral? Or like
You do. Yeah. So.
Like the entry, I don't know, maybe split.
Yeah, there's a choice of orientation that's involved when you interpret these cuts as quantum states, because if I give you some field data 5x and I tell you to put that field data here, there's a choice of orientation in how you implement that boundary condition. And if we wanted to actually write some totally precise formulas and actually calculate these wave functions, we'd have to be careful about the orientation, and it would enter exactly in the way that you're saying, and there would be some complex conjugation involved in going between the two pictures. No. Other questions? So that's thermofield double. I want to say a few more words about it because I like to think about it a certain way. So I like to think about this as created by evolving the maximally entangled state. Okay, so what is the maximally entangled state? The maximally entangled state is just the one that looks like this. It's the infinite temperature state. This is even worse. Okay, this is even more badly defined because the sum diverges. But we can think of this formally as a maximally entangled state. This corresponds to the operator, the identity operator, of course, in one copy. So formally, as a path integral, the maximally entangled state is the path integral on the strip of size 0. Okay, so this is height 0. Because it has inverse, it's like a thermal state with inverse temperature 0. Okay, so, and that makes a lot of sense, because if I put field data phi 2 here and phi 1 there, then what's the path integral going to do? It's just going to give a delta function that says that phi 1 has to equal phi 2 when you bring these two things together. So that really is the identity operator. So the path integral on the nothing strip is the maximally mixed state. And then we can think of this thermofield double state beta as coming from evolving this by beta over 4 on one of the cuts and beta over 4 on the other cut. So I'm using H1 and H2 just to denote the Hamiltonian acting on the two copies of the Hilbert space. Okay, so what does Euclidean evolution by the Hamiltonian do? It just makes the strip longer. So we start with a state on the nothing strip. Then we evolve by beta over 4 up this way. And we evolve by beta over 4 down that way. And that gives our path integral for the thermofield double on a strip of size beta over 2. Yeah?
So instead of picking beta over 4 and beta over 4, you could have picked
Sure.
anything that added to beta over 2.
That's right. Yep. Okay, good. So I just like to think about the thermofield double this way. It gives you some intuition for what this state is like. Okay, if you take infinite temperature, this is a state where everything is perfectly correlated between top and bottom. When you evolve in Euclidean time, what that does is it kind of spreads stuff out. Not in the sharp way that happens in Lorentzian signature. So in Lorentzian signature, when you evolve by the Hamiltonian, stuff spreads out in the light cone. That's not what happens in Euclidean, but it does sort of spread out on distances of size beta. Okay, so actually the Hamiltonian spreads stuff out. It's not a sharp light cone. There'll be exponential tails that go further than beta. But it roughly is spreading things out on size beta. So the two sides of this state will still be well correlated on distances less than beta, but they'll basically be, sorry, do I have it backwards? They'll be well correlated on distances less than beta, but not correlated on distances greater than beta. Okay. Questions? Yeah.
Is it actually called the nothing strip? Or is
No.
it just
Well, sometimes people call it the infinite temperature state, or the maximally entangled state. It's not called the nothing strip. That was just me. Anything
So
else?
when you take the other limit, the beta going to infinity limit,
Yeah.
that is 0 temperature limit, so it will give you the vacuum state, or the outer product between vacuum ket and
Yeah, let's see. Well, I'm not sure what it means to take them both to infinity. If you freeze one of them and take the other one to infinity, then yeah, you'll just get the vacuum state.
No, from that picture you wrote down, extend both of them.
Well, these have open cuts. Sorry, I should have drawn these as open because it's a quantum state. And you can't exactly take your open cut and push it to infinity because then
I
don't know how to interpret that picture anymore.
Well, you could imagine taking beta to 0, and then you would skip the ground state.
Well, this is a quantum state on two copies of the Hilbert space. So there isn't really a.
So taking.
I mean, we'd have to put in. Well, if we want to get the ground state from here, the way to do it would be to put some field data on the bottom cut. This is now a quantum state in one copy of the Hilbert space, and then send that bottom cut to infinity. And then when you do that, the quantum state the field data that you put there will wash out. It won't matter. So that'll give you the vacuum state here.
Sure, but you can also, without looking at the picture, you could just look at the equation above it, and then if you sent both betas to infinity, you would get 2 copies of the ground state.
No, I'm saying you wouldn't get that because I don't know what that picture means as a path integral. Like if you put this at infinity, the cuts are at infinity. Like I don't know what that means.
I'm just saying, so max is just like a superposition of all of the states.
Yeah.
One of them is the ground state, and then if you send both betas to infinity, that's going to be the one that survives from those exponentials.
Oh, you mean the 0, 0 state?
Yeah.
That's true. Yeah, if you send these very far apart, but you keep the cuts, you'll have the 0, 0
Right.
product state. That's
Yeah.
right. Okay. Now going back to our discussion of Rindler space, I want to connect these, and I think many of you have anticipated where I'm headed with this. The statement is that the Minkowski vacuum is the Rindler thermofield double. Well, I already wrote it. Let's write an equation. So the claim is that 0 in Minkowski is beta equals 2 pi in the Hilbert space Rindler times Rindler. So if I draw a picture of Minkowski space here, with time going up, then I cut it at time 0, then the Minkowski vacuum, of course, is defined on all of space. So it includes both left and right Rindler wedges. So there's 2 copies of the Rindler-Hilbert. You need to put together 2 copies of the Rindler-Hilbert space in order to talk about states in Minkowski. And for this special choice of state in the vacuum state, the claim is that you can interpret it this way. So the derivation is easy. Now that we've got everything set up, we can derive this in one line. So let's start by writing the Minkowski vacuum as a path integral. Well, there it is. It's the path integral on RD minus 1 times the half line. So path integral on the lower half plane in 2 dimensions. And now we're done. Okay, so we're just going to take this path integral and reinterpret it. To reinterpret it, we're going to think of the angular direction, the theta direction, as time. Okay, so time goes around this way, which means that time a little bit spatial slices. Space looks like this. So what is this manifold? If I draw it just on the, so let's call this direction theta, and we'll call the outward direction, call this r. So if I draw this on the r theta, in r theta coordinates, then what does it look like? Well, there's a half line, r, and there's a strip in the theta direction of size pi. Theta runs from 0 to pi. And when we use this path integral picture to calculate matrix elements, what do? We insert some field data on this cut up here, which I can think of as being a phi 2 on the left and a phi 1 on the right. If we draw that on the theta r plane, that means we're putting a phi 1 down here, phi 2 up there. But this picture is exactly the picture for the thermofield double state that we just said. So this is the state beta equals 2 pi. That is the state sum over n. N is a Rindler, is a eigenstate in Rindler space, e to minus pi Ka and n where Ka is the conserved charge associated to rotations. Euclidean rotations, which are Lorentzian boosts. Okay, so 0 in Minkowski is this state in Rindler, which is exactly the thermofield double state, and in particular gives us back, by now taking the partial trace, we can trace out one of the Rindler regions. By taking the partial trace, we're going to get back the thermal density matrix in the other Rindler. Questions? Yes?
How are we supposed to interpret the boundary condition on that path integral diagram you're drawing at the junction at r equals 0? From a purely like path integral sense.
Yeah, that's tricky. Let's
The
see.
second diagram makes sense.
If you really want to make sense of this splitting, you have to regulate it. Okay, and this comes back to this thing I keep sweeping under the rug about UV divergences and regulating and QFT. If you really want to make sense of this, you have to cut out a little piece of the manifold and regulate it like this and talk about and worry about boundary conditions there and any contributions that might have to your calculations. And when we actually do calculations, we're going to have to worry about that. It contributes. Okay, I'm not sure. Did this make sense? We're happy with the thermofield double. Rindler equals thermofield double. Minkowski vacuum. Yeah.
I mean, I guess I'm a little confused about the process
Yeah.
of what you just did. So you drew the picture that corresponds to the vacuum state of Minkowski, and we knew what that meant. Like you specified some boundary data at the bottom, and then you evolved it in Euclidean time, and you left an open cut for the other side of the thing.
Yeah.
And then you said something like, now we're going to reinterpret this.
Yeah. Let me put it this way. There's a way of translating quantum states and operators and the whole operator formalism into path integrals. Right? That's step one, where we took this quantum state, or you can think of it as a matrix, as a wave function if we put in some data here. And we translated that into path integrals. That's the black marker here.
Right.
Okay. Now there's an inverse of this, where you take a path integral and you chop it up you say what you mean by space, and you now have a Hilbert space interpretation with operators and states and so on. The point here, and the whole reason this does something non-trivial, is that many times there's more than one way to chop the path integral.
Right.
So
then
you don't necessarily come back, you don't necessarily get the thing that you started with.
So then in what sense is it like an equal sign? You know what I mean?
It's really truly an equal sign. What I mean is, there's two, so when I draw it as a state, it's a little abstract. So let me write it as a equation with numbers.
Uh-huh.
So for an equation with numbers, the statement is that the ground state wave function in Minkowski. So Minkowski space has a ground state wave functional, which depends on field data on all of space. Let's see if I can get this right. Okay, now in terms of our path integral, that's phi of x overlap 0 Minkowski. And this path integral argument and reslicing, what that tells us is that this overlap is equal to phi of x restricted to x1 greater than 0, viewed as a Rindler state. Okay, so I'm taking that same field data, and what I just wrote is phi 1. It's the right half of the field data. And then evolved by e to the minus pi k. And then we put the other field data on the other end. So then we have phi of x with x1 less than 0 on the left, where now that's also viewed as a Rindler state. Does that make more sense? That's it. So this transition amplitude is just being reinterpreted as this transition amplitude.
And is it easy to see how you get from the first line to the next without drawing pictures?
Oh, without drawing pictures. You're handicapped. It's not easy. No, it's not easy. You know, it can certainly be done. They didn't draw any pictures in the early papers on this. So the paper of Unruh does this all in terms of like A and A dagger and B dagger and the Bogolyubov transformation that you read about in Carroll. In the early work of Visignano and Wickman, who also derived this statement, they do it using some pretty formal properties of algebraic quantum field theory, which are equivalent to these path integral pictures that I'm drawing, but way harder to read. Yeah.
I have two questions. So in this first picture at the top, this is a semi-infinite interval, right? For the top diagram?
Yeah.
And so that translates into R going off to infinity in the lower line, or lower diagram?
Yeah, so here this is, R goes off to infinity.
Yeah. Okay.
Yeah.
And then the other thing was, it looks like, so if the Rindler states capture stuff that's in the Rindler wedges, what about the quote-unquote behind the horizon region?
Oh, this part up here?
Yeah, the one below.
Yeah, let me say a couple words about that. Well, this kind of fits into what I was going to say next, so let me I'll try to make sure I mention it, but stop me if I don't. Okay, so let me just kind of recap the situation and give a few words of interpretation here. So here's Minkowski space. We have taken space at time 0 and cut it into two pieces, B and A. So time is going up here. Now, we derive the density matrix on the slice A, but because it's a relativistic Q of T and it's causal, that actually tells us not only about A, but about everything in the diamond associated to A. Okay, so this Rindler density matrix that we derived, it really tells us everything about this diamond. And there's another one that tells us everything about that diamond. And to summarize the concept underlying those equations, it's the following. In the Q of T vacuum, 0M, 0 Minkowski, B and A are highly entangled. Why are they highly entangled? Well, that's the thermofield double state. The thermofield double state is an entangled state between the two sides. And in fact, we haven't talked yet about measures of entanglement, but if you try to measure this entanglement, there's actually infinite amount of entanglement at short distances. So that's happening here. At this point here, things slightly to the right are entangled with things slightly to the left. And as we go to higher and higher energies, there's an infinite number of modes. If we think about shorter and shorter distance here, there's an infinite number of modes. They're all entangled across the cut. So there's actually infinite amount of entanglement at short distances between here. And then there's also a finite amount of entanglement at long distances between the long distance modes on the two sides. And this is why, well, two important things. First of all, this is why rho A looks thermal. Yeah.
So when you talk about the entanglement between a particular part of space and another part of space, what do you mean by that? Because we're already talking about you could compute the total entanglement by computing the von Neumann entropy of the reduced density matrix.
No, what I mean is that we have this mode is entangled with that mode.
But those modes are not localized, are they?
These are Rindler plane waves.
Okay.
But we could, so these states are Rindler plane waves because they're energy eigenstates in the Rindler sense. So these are Rindler plane waves, but we could make wave packets and localize them and assign them a position in space. And it's not that there's literally some entanglement between like here and here, but we could make wave packets that are supported mostly on a certain set of modes, and then we could ask how they're entangled in this state. I think that's the way to think about it, yeah. Okay, I'm still circling around Ibrahim's question though. Let me continue and then we can come back if there's more. So, okay, so this is why rho A looks thermal. It's because we took something that was entangled and then it was highly entangled and then we traced out half of it. Okay, you're going to get something mixed if you do that. This is also why in quantum field theory, phi of x at t equals 0 and 5y at t equals 0, does not equal 0. Okay? It's always a little confusing when you first start learning quantum field theory that these two-point functions are non-zero spatial separation, space-like separation when there can be no causal influence. Well, there's no causal influence between region B and region A, but there are correlations between region B and region A, and those correlations are understood here as the entanglement between the two sides. So it's the entanglement between the two sides that produces those correlations. Okay, so these, I just want to emphasize that this entanglement and thermality is just very basic and fundamental and essential to quantum fields in general. That we have this large amount of entanglement. It's responsible for the space-like correlations and also responsible for the Rindler thermality. Yeah.
Can you say again why you're mentioning causality in this? I thought the correlator, so that just only was true with commutators.
Yeah, causality is proved by commutators. This is not a commutator, so this is why it's allowed to be non-zero. And then you could ask, well, what is it measuring then if it's not measuring some particle moving from here to there? Well, what it's measuring is the existing correlations in the quantum state at time 0. And how can you have some correlations? Well, it's because it's an entangled state between left and right. Yeah.
Is the entanglement going from infinity and reducing from short distance to large distances, is that related to the Hamiltonian spreading states up earlier?
Sorry, so is the what? Say the first half again?
The entanglement reducing from short distances to large distances.
What do you mean by reducing?
Or if it's infinity at short distance and
Oh.
less entanglement, sorry.
Yeah. Yes. Yeah. If we that's exactly right, because if we take this diagram that I drew before that looks like this, then if we only evolve a tiny bit, it's perfectly entangled. That would create a maximally entangled state. When we evolve around, the stuff that's near the origin only goes through a little bit of Euclidean evolution and stays near maximally entangled. Whereas the stuff that goes further undergoes more Euclidean evolution and gets spread out more and is less entangled.
But they all go through the same angle, and it's the angle that you drew in the other picture as the time axis. It's not the coordinate distance that controls how damped it gets. It's the physical distance that controls how damped it gets. But in the equation with the Ka, it's like it doesn't look like that. Depends on where it is. That's just the generator of these rotations.
But this will be reflected in the fact that a wave packet out here will have support in the high energy Rindler modes. So it'll have less entanglement in the thermofield double state. It's sorry, do I have it backwards? I might have that backwards.
Oh yeah, I guess it would be.
We'd have to look at wave packets, and I can't do that in real time, but yeah. So let me circle back to this question about this region up here. Well, you can't learn about this region knowing only the density matrix in A or only the density matrix in B. The only way to learn about it is to know about both A and B. So one way of thinking about it is that stuff that happens up here reflects the details of the entanglement between A and B. The fact that the state is thermal in A yeah, let me just leave it at that. It's the details of the entanglement between A and B. You really need both states to put them back together into one big state in order to be able to talk about stuff up here. Yeah?
If you compare this to bringing together two systems of spins, is there any analog for the two regions apart from 1 and 2 that I've been talking about?
You mean for the joint region? Yeah, if you were to do this in a non-relativistic system, like a spin chain, then basically these light cones would just, the speed of light is effectively infinite. I mean, not really, but roughly speaking, these light cones would kind of collapse to here because the speed of light is infinite. It's not quite true. Even in spin chains, there's an effective speed of light, which is called the Lieb-Robinson velocity. It's not a strict speed limit, like the speed of light. It's sort of a rough speed limit, and you can get exponential tails outside there. So I guess there is some sort of approximate structure that looks kind of like this, even in a spin chain, but yeah. Things can go fast, so it's not as clean cut. Other questions? Happy with the thermofield though? Under radiation. Pictures make sense.
Can we say something general about the correlation in the sense that is it like sort of universal or something?
You mean how big that correlation is?
Yeah. Do we need the full theory to calculate such correlations, or is there some universality property because this is controlled by short distance behavior?
Symmetries, right? CFT gets us pretty far, even if you just tell me the symmetries of this area. That actually.
Well,
I mean, CFT, I guess that is fixed.
Even in general, I mean, yes. Although I'd have to. Okay, I can give the answer, but I can't immediately relate it to this discussion of entanglement in any kind of quantitative way. But space-like correlations at short distance are always singular. Okay, that kind of makes sense. Everything is infinitely correlated, so as you bring them together, there's a singularity. The strength of that singularity depends on only on the scaling dimension of the operator in the UV. If we take so that's in the short distance limit. There's also universality in the long distance limit. In the long distance limit, the 2-point function is set by the mass gap. It's exponentially suppressed in a way that's set by the mass gap. We could derive that by looking at the path integral and chopping it in Euclidean and then projecting onto the lowest state in that Euclidean path integral. Of course, if the theory is gapless, then things are a little different. Like if it's conformal, you get power law at long distances. And all these facts have corresponding facts in the entanglement structure. Okay, so gap theories have basically zero entanglement at short distance as you go to long distances. Gapless theories have sort of goes off in a power law way, like it's smaller at short distances, but it doesn't exponentially go to zero. And as we said, both the 2-point singularities and the entanglement is infinite as you bring points together. So the two kind of go hand in hand. Okay, these pictures are pretty important. make sure you review the notes and the readings that I put on the webpage, because this was just warm up. We're still doing warm up. Okay, so these it takes time to get used to these pictures, I know, but we're gonna have a lot more of them, and they're gonna get a lot more complicated. Okay, so we gotta like practice going through it, and I can do more questions if it would be helpful, or we can discuss afterward and make sure these pictures make sense. Yeah.
So when you said that the stuff that happens inside or behind the horizon is sort of captured by the time, or like the correlations between regions A and B, is that kind of like saying that it's controlled by data that you specify at the origin or in the neighborhood of the origin?
Well, that's part of it. Yeah. I mean, you really have to know it everywhere. You have to know it everywhere.
Yeah, it's just that it's only in the causal future of that point, right? Causal future, causal possible.
Well, it's also in the causal future of this point.
Yeah.
So you really have to know it. You have to know it everywhere to go into that region. Okay. We're going to have a change of gears. So the next thing we're going to do, let's find a better marker. The next thing we're going to do is discuss the laws of black hole thermodynamics. So we're going to set aside what we've been doing for a lecture or so, and review or just introduce these laws. If you took my GR course a couple years ago, which I know many of you did, then we're going to redo that course in like one lecture. That's the plan. We'll skip some of the details. Okay, so first thing I want to do is to review charged black holes in four-dimensional gravity. I'm going to assume that you've seen black holes before. I am going to...
Not in person, of course. Not
well, yes. I'm going to sort of assume that you've seen charged black holes before, although that's not essential. I think I'll explain them. But, okay, so this is like basically to help you remember this stuff and to set some notation, to set up the aspects that we need here, but pause me if you want more explanations. Okay, so let's consider Einstein-Maxwell theory in 4D, and I'll set G Newton to 1. So the action I is 1 over 16 pi, integral d4x, root minus g, r minus f mu nu, f mu nu. The equations of motion, of course, are the Einstein equation. G mu nu is 8 pi T mu nu, and grad mu f mu nu is equal to 0. There's a solution of these equations of motion, which is a charged black hole. It's called the Riester-Nordström solution. And here it is. The metric is ds squared is minus f of r dt squared plus dr squared over f of r plus r squared d omega squared. F of r is the function 1 minus 2m over r plus q squared over r squared. The vector potential A, which I'm writing as a 1 form, so A mu dx mu, is minus q over r dt. And if you calculate the field strength from that, it has one non-zero component, FRT, and its antisymmetric version, which is the, remember the T components of F are the electric field. Okay, so this is a electric field in the radial direction. And that's q over r squared. And that's it. So this is the Ricci-Nordstrom solution. This is a charged black hole. And what we're going to do is we're going to use this as an example to study the laws of black hole thermodynamics. This is the simplest, in many ways, the simplest example that we can look at that still has all the good stuff in it. Questions so far? Okay, so there's a couple of parameters in this metric, m and q. I give them those names because they're the mass and charge, but we don't get to just declare that. So how do we know that those are the mass and charge? Well, the charge is easy. We can measure charge using the Gauss law by calculating the flux far away. And in fact, that is exactly the electric field of a point charge, of charge q. So Gauss law, of course, is going to tell you that this has charge q. So the charge is easy. What about the mass? Well, in general relativity, there's something like a Gauss law, but for energy, okay? Because the metric responds to energy. And so using the metric near infinity, you can measure the total energy in the space-time, similar to the Gauss law. We don't have to actually do the calculation because we can use the following trick. We just go to large distances, very far away from the black hole, and then we compare to Schwarzschild. So if we go to large distances, r much greater than m, then the metric is approximately the Schwarzschild metric. The extra non-Schwarzschild terms in the metric, the q terms, those are subleading. Those don't enter into the asymptotic components of the metric. So the leading asymptotics of this metric are Schwarzschild, and therefore the metric has mass m. You could think of this as a gravitational Gauss law. A couple comments. First of all, this is a solution of the source-free Einstein-Maxwell equations. I did not put any charged particles or charged stuff or any of that kind of thing. It was just the gauge field and the metric. So there are no charges anywhere. It's the geometry itself that's charged in the recent Nordstrom black hole. Now we could quibble about r equals 0. Is there a charge at r equals 0? Well, it kind of looks like it. If we were to look at the Maxwell equations there, it looks like there's a source at r equals 0 because it's the electric field of a point charge. But r equals 0 is a singularity, and we're not allowed to talk about it. It's just excluded. We can't say that there's charges there. But that's effectively where the charge in the space-time is coming from. Yeah.
So black holes can have like electromagnetic charge. Can they be charged under other gauge groups?
Sure. Yeah. Yep.
And do we have like solutions for those?
Well, it's okay. So let me go back. In the real world, the answer is no. Okay. So in the real world, the only unbroken gauge group is electromagnetism. Is U1. So sorry. There's also QCD, but QCD is confining. So the only unbroken gauge symmetry for which the classical solutions of the classical equations are a good guide to the behavior of the quantum theory is electromagnetism. Okay, so in the real world, we only talk about charged black holes. Now, if you really want to be nitpicky about it, there are no charged black holes, no U1 charged black holes in the real world either, because if you had a recent Nordstrom black hole in outer space, the charge would be so strong that it would just pair create charges out of the vacuum, and it would very quickly neutralize itself. So you can't actually make one. But you can find, if you have, say, a classical Yang-Mills field, then you can find solutions, charge solutions. But if it's confining, they just, for the usual reasons, they don't really tell you anything about the quantum theory. Yeah.
So in the usual flat space electromagnetism, if we put a delta function in the origin, we get that corresponds to having a point charge.
Yeah.
And you can take that outside, like make a whole space, and that is still the solution because that's points. Like that's a function.
Agreed.
So in what sense is space-time charged? Because actually we have the same situation as in flat space. Just those charged in the center. Or that it's equivalent with saying there's a delta function in the center, which is look up because it's singularity.
It's the same as that. It's
Okay.
the same as that. Yeah.
So in the end, we don't know what the singularity is. So what the charge is a mystery.
Yeah, if you actually make one of these, like by collapsing some charged matter, then you will have charged matter inside the black hole, and that'll provide the source for Maxwell equations. My point was, yeah, you can think of the singularity as being charged. I think that's not a great way to think about it because we shouldn't talk about the singularity. Or you can think that somewhere deep inside the black hole, there's some charged matter, but then you better change the equations of motion and deal with it. So it's not so different from what you're saying. So this spacetime has two horizons. To find them, we take that metric function f of r and we write it as, we just factor it. It's 1 over r squared times r minus r plus. And this r minus r minus, where r plus minus is equal to m plus or minus the square root of m squared minus q squared. So there are two horizons. There's an outer horizon, r plus. There's an inner horizon, r minus. the cosmic censorship conjecture states that in reasonable space, it states that under reasonable initial conditions, well, let me say the informal version of the conjecture first. The informal version is no naked singularities. Okay. In other words, all singularities must be hidden by a horizon. Well, what do you mean by must? I can, if I set Q to be bigger than M here, then there are no horizons in the actual space-time because these horizons become complex. So there are no horizons, but there's still a singularity at r equals 0. Okay, so the Q greater than M Research-Nordstrom black hole is a naked singularity. There's nothing particularly wrong with it as a solution of general relativity, or Einstein-Maxwell rather. However, we think it doesn't make sense. So the cosmic censorship conjecture formalizes that. The conjecture is that naked singularities do not form from reasonable initial data. If I could add like a cosmic censorship prime conjecture, it's that in quantum gravity, we don't need to understand naked singularities because they just probably don't exist in the quantum theory. Yeah.
So what I thought you told me once about Reisner-Nordstrom is that it's not much of a conjecture for Reisner-Nordstrom because if you try to make a super extreme black hole by throwing something in, you just won't be able to. Like, it's just dynamically forbidden. So, I mean, I don't see why you have to impose cosmic censorship to say that you couldn't have this.
That's true. Okay, so it's true in the linearized theory that you can check this. Like you can create a black hole that has small q, and then you can try to drop some charges into it in a linearized way and solve for the back reaction and see if the black hole ever violates this bound, and it does not. What I think you need the conjecture for, even for Reisner-Nordstrom, is like if I just declare that there's some crazy nonlinear initial conditions with crazy metric and crazy gauge fields, I don't think we can prove it in that case. And if I allow charged matter also, then I'm almost certain that we can't prove it for arbitrary nonlinear initial conditions.
Okay. Is it wrong?
Is it wrong? Is cosmic censorship?
Well, it's just for Reisner-Nordstrom in fourth dimension. Is it that you can't prove it, or that it's actually not true?
Well, I think the answer is that it's morally true, but it might not be technically true. And what I mean by that is that there's some sense in which it's true, but I'm not certain that we know the mathematical assumptions that are required to prove it. Like what the theorem, I'm not sure that the theorem has been stated in the true way. And the reason I said, people who study this might disagree with me, but the history is that this conjecture was made in a more general way, and counterexamples have been found, but there's always some excuse, like that they had non-generic initial conditions or something like that.
Or it was like a mild violation or something.
Yeah, like a very finely tuned one. So I think the current versions of the conjecture involve some technical assumptions about genericity of the initial conditions. Those very well might be just plain true for four-dimensional Reisner-Nordstrom. They're not true for five-dimensional black holes. We know counterexamples for five-dimensional black holes. But even in that case, they're morally true in the sense that...
those ones were the kind of mild ones where you sort of just like pinch off, but you still have predictability and stuff.
That's right. So that's why I'm counting it as there's definitely naked singularities in 5 dimensions. They've been found through numerical GR and understood to some extent analytically. But there's a sense in which they don't count, like they're not bad. So it's one of these like, well, the conjecture wasn't literally true, but the feeling of the conjecture was true. The naked singularities that have been found in 5 dimensions sort of appear in such a way that that only like 1 or 2 Planck scale quanta can escape from them before they disappear. Now the problem with naked singularities, if you have a singularity like this and you live here, the problem with naked singularities is that you need quantum gravity to understand them. And even if you're a low energy observer who sits very far away from a black hole, you might be able to learn lots about the Planck scale just by staring at one of these naked singularities. Now that would be great. I would love to do that, but it's kind of too good to be true. And it would probably not make sense as a quantum theory. These naked singularities that exist in 5 dimensions only exist for an instant. And if that instant is not long enough to contradict this intuition. Yeah.
Isn't the Big Bang a naked singularity?
Yeah, it is. Yeah, the Big Bang is a naked singularity. It didn't form from generic initial conditions. I mean, so I think it's important to clarify here that cosmic censorship is, at least the way we usually talk about it, it's a conjecture about PDEs. Right? It's a conjecture about classical solutions of equations of motion of gravity coupled to matter. And when we go near a singularity, PDEs are probably just not relevant in any way whatsoever if you get close enough to the singularity, because then you need to be doing quantum gravity, not solving PDEs. Okay, so you could ask whether there's a quantum cosmic censorship conjecture or something along those lines, but it would have to take a very different form. You couldn't even phrase it in the way that it's usually phrased. Okay, anything else? So, cosmic censorship tells you that the magnitude of charge is bounded by the mass. A black hole is called extremal if it saturates the cosmic censorship conjecture. Q is equal to M. Extremal black holes might sound kind of weird and special, and they are, but they're also very important for theoretical purposes because they're sort of the simplest black holes in quantum gravity. And we'll come to that later. I want to draw the Penrose diagram for Reese and Nordstrom. It's already here on the blackboard. You probably have seen it, but I want to review this quickly because everyone always forgets what Penrose diagrams are. So we're going to start with a couple of warm-up Penrose diagrams. The first is two-dimensional Minkowski space, R1, 1. The metric is minus dt squared plus dx squared, or in null coordinates, minus dt plus dt minus, where t plus minus is t plus minus x. So these null coordinates point like this. T plus to the left, I think. No. Did I get it right? Other way. T minus to the left, T plus to the right. So what is a Penrose diagram? Well, we'd like to draw a picture of this space-time. Now, T plus minus run from minus infinity to infinity, and it's hard to draw a picture of infinity. Instead, we define, we just take an arctan. Okay, so let's define u plus minus to be arctan of t plus minus. And well, this is just a new coordinate. I'm just changing coordinate systems. What's so great about this new one? Well, the great thing about this is that arctan runs only from minus pi over 2 to pi over 2, and that's easier to draw. So the metric in these coordinates is obtained just by plugging this in. And what you'll find is minus omega squared du plus du minus, where the conformal factor, omega squared, is 1 plus u plus squared to the minus 2, 1 plus u minus squared to the minus 2. Sorry, those were both minus 1. Okay, so let's draw a picture of the space-time. Well, I want to make it look like a. Well, I want time to go up. So I'm going to draw the. U plus and U minus directions going this way. So this one is U minus, and this one is U plus. Now, I've been drawing lots of pictures of like square things and stuff when we did path integrals, and they were all kind of schematic because that was always infinite spaces, and I was drawing them on the board. But now, when you draw a Penrose diagram, and when I draw this diamond, I literally mean it looks like this, because this is a box of size pi in the two directions, because u plus and u minus are running from minus pi over 2 to pi over 2. So I mean this diagram literally now, unlike all these cartoons. So this is our Penrose diagram for R1, 1. What's special about it and what makes it a Penrose diagram is that light goes at 45 degrees. Okay, so let's check that. A null ray has ds squared equals 0. So if we either fix u plus and look at a light ray in the u minus direction, or vice versa, that'll be a null ray. Okay, so this is a null. This is a null geodesic, path of a photon. And this is also a path of a photon. And they go at 45 degrees on the diagram. And of course, I'm doing flat space-time right now, so that's just what we're used to. It's a space-time diagram. Stuff goes at 45 degrees. But the point of Penrose diagrams is that we'll do that even when the space-time is curved. And the advantage is that it becomes very easy to understand the causal structure of the diagram of the space-time just by looking at the diagram. Okay, so can you get from here to here? No. Obviously not. That's not so easy if I were to draw a diagram in Schwarzschild coordinates. You would have to do a calculation. So that's the point of the Penrose diagram. Massive particles on the Penrose diagram. Well, let me label and name a few things. So this thing down here is called I minus. That's past infinity. Past time-like infinity, sometimes it's called. This point up here is I plus. It's future time-like infinity. These are called past and future time-like infinity because things that travel on time-like world lines end up there. Like if you have a massive object, like a rocket ship that went on some missions and then flew around for a while, its world line might look something like that. This point out here is called I0. That's space-like infinity. You can't get there. Sorry. This line up here is called scry plus. The one back here is called scry minus. I don't know how to draw scry, so I make that funny I instead. And that's called future null infinity and past null infinity. You can't get there, but a photon can. You can get there if you happen to have a rocket booster with an infinite amount of fuel. Because, let me draw a new picture quickly. So, Grindler space, we can draw in this diagram as the wedge on the right. Good. So we're just kind of squishing the usual diagrams all onto one page. All right, let's stop there. We'll continue with this next time. I can do questions. People want to hang out.